Okay, so now that we've talked a little bit about the basic properties of acids and bases, the strengths of acids and bases, and now this new idea of the ionization of water, we're ready to move on to something that you've probably already heard before with respect to acids, maybe not so much with bases, but we'll talk now about the pH scale. And there's all sort of mention of the pH scale. There was a popular commercial some decades ago that would talk about the secret deodorant as strong enough for a man but pH balanced for a woman. So this was getting at the idea that there's a slightly different pH, but again, it was over-exaggerating that idea. So you've probably heard the pH scale in a lot of non-science situations like that. Well, now we're ready to explore it in a scientific sense if you've never done so before. Okay, so the pH of a solution is used to indicate the acidity of that solution. So in particular, pH stands for the power of hydrogen, pouvoir d'hydrogène in the French. So that's where that little p and the capital H come from. In terms of our course, it's going to have values that range from 0 to 14, representing the H3O plus concentration of a solution. There are solutions that have pHs of less than 0. You can get into negative pHs, and there are solutions with pHs greater than 14, but in our course, we'll stick to that 0 to 14 range. So that's a good thing to know, especially as we get into the calculations. pH of a solution is acidic when the values are less than 7. Again, we're always talking about 25 degrees Celsius, which we'll consider to be our standard temperature here. It's neutral with a pH of exactly 7, and that solution would be basic when the pH values are greater than 7. So these are some ballpark ideas about pH, and then we'll get into the true details of what the pH value actually means in terms of the concentration of H3O plus for a solution. So here we see some pH values for everyday substances. You see that pH of 0 for a 1 molar hydrochloric acid solution. So if we have a stronger hydrochloric acid or some sort of superacid, which do exist if you go on in chemistry, we would easily go below 0 in terms of a pH value that would be negative. But for our course, again, that 0 value is where we're going to stop. And as we look up, we go to 14 would be a 1 molar NaOH solution. NaOH or KOH, either one or the combination is often referred to as lye in everyday language. But we could certainly have a more concentrated NaOH solution or a super base that could go above 14, but like I said, we'll stick in that range for our course. And that's because there's lots of things that fall in that range, especially in terms of everyday substances, particularly biological substances. Gastric juice, for instance, our second item from the top, it has a pH of about 1.6, and there is hydrochloric acid in that gastric juice, the solution in our stomachs, and it's quite acidic, as you can see. Lemon juice itself, which you know we can consume, that's something that people will put in various recipes. It's pretty acidic at a pH of 2.2. Again, when we go up a pH value, we're actually decreasing our our H3O plus concentration by 1/10 for every pH unit we increase. So this means that it's a fair deal less concentrated in H3O plus compared with that 1 molar HCl solution, but still quite a bit of H3O plus around. And as we go up, we see some other foods. Lots of foods tend to be acidic. Urine there, its average is around 6.0, but it could be lower or higher for a given individual. So as we go up to plain old pure water, that's our pH 7.0. Drinking water tends to be a little more basic than that, around 7.2. Blood tends to be basic and tightly controlled around a pH of about 7.4. Bile, another biological fluid there, is 8.0, and we go up from there. Finally to that NaOH solution. So there you have it, a number of everyday substances and their relative pH. We already mentioned this value of pH being acidic when it's less than 7, neutral at exactly 7.0, and basic above pH 7.0. Again, that's for 25 degrees Celsius solutions. If the temperature changes, that pH value would also change slightly, but that's where we tend to be most of the time in this course. So in terms of H3O plus concentration, what a pH less than 7 means is your H3O plus concentration is greater than 1.0 times 10 to the minus 7 molar. So anything above that value would be acidic. For a neutral solution, that means the H0 plus at 25 degrees Celsius has a concentration of 1.0 times 10 to the minus 7 molar, which should look familiar. That's from that kW of water that we talked about last chapter section. And then finally, anything above that at 25 degrees Celsius would have an H0 plus concentration less than that 1.0 times 10 to the minus 7 molar. So as pH increases, the concentration of H0 plus actually decreases. So that does sometimes take students a little bit to get used to. So hopefully you realize that we're really doing a mathematical operation, and once we define that, then I think this will all make more sense to you. All right, before we define pH, we'll talk a little bit about how it's measured. And there's a number of different ways, some a little more exact, some a little less exact, but all give you a reasonably reliable value for pH. A pH meter would probably be the most precise way to measure pH. Again, notice I said precise and not accurate. There is a difference there. If the pH meter is not standardized against some known concentration solutions, it is not necessarily very accurate, although it may be precise. You may get reasonable values close to each other, but they may be fairly far from reality. So pH meters rely on a glass electrode, and if that electrode's not taken care of and not standardized against solutions of known pH, then you could have some very unreliable data from those. Even though they look nice and they seem to give you a very exact value, you should always be careful to make sure you trust your pH meter. pH papers have been around for a long time, and they can be found that have specific color changes when placed in solutions of different pH values, like we see in that middle picture there. There's also test papers with a color comparison chart that we see where you can at least get a reasonable value between, say, pH 0 and 11 on those papers. If it was less than 0 or greater than 11, you wouldn't see a color change, though, so that is a drawback there. Finally, indicators that change color with pH have been very useful throughout the history of chemistry, and a couple that we'll talk about in detail will have to do with some key color changes, but again, that's a nice notable color change at a specific pH, so those work well for things like titrations. So these are all valuable and valid ways of measuring pH. All right, so one last thing before we move into calculating pH, let's take a look and see how you're doing with the concept of pH, and hopefully that concept will get even better once we talk about exactly calculating the pH. So in this learning check, you're asked to identify each solution as acidic, basic, or neutral. So for each of those, go ahead and read the description and decide whether you're going to call it A for acidic, B for basic, or N for neutral, or just spell out the words, whatever you prefer to do. Pause the video here while you do that, and then start back up once you think you have all your answers correct. All right, so HCl, a very strong acid with a pH of 1.5, so that's less than 7.0. We'll assume that we're at 25 degrees Celsius for all of this work, and that is definitely acidic. B, pancreatic fluid, H3O plus concentration of 1 times 10 to the minus 8 molar. If you recall, we said 1 times 10 to the minus 7 molar H0 plus concentration is neutral at 25 degrees Celsius. This is a smaller concentration of H0 plus, so that means we must be basic. For C, Sprite soft drink has a pH of 3.0. Just like A, we have a pH less than 7.0, so we would expect it to be acidic. D, a pH of exactly 7.0 should be neutral. E, an OH minus concentration of 3 times 10 to the minus 10 molar. Now, if you recall, for neutral water at 25 degrees Celsius, that OH minus concentration equaled the H0 plus concentration, which equaled 1.0 times 10 to the minus 7. So here we have a smaller concentration of OH minus, which means we must have a greater concentration of H0 plus, and therefore must be acidic. Finally, for F, now we have an H3O plus concentration that's smaller than 1 times 10 to the minus 7, 5 times 10 to the minus 12, so that must be basic. So hopefully those all went very well. If you missed one or two, hopefully the explanation here has made you understand what went wrong. If that's not the case, if you're still struggling, you missed a number of these and you're not sure why, please do reach out to me for some guidance. Okay, finally, here we are defining pH so that you'll be able to use this pH relationship to calculate pH. So pH is, mathematically speaking, the negative logarithm, the base 10 log, of the H3O plus concentration. So there it is, pH equals minus log of H3O plus concentration. So for a solution with an H3O plus concentration of 1 times 10 to the minus 4 molar, if we plug that into our calculator, the pH equals minus log of 1 times 10 to the minus 4 molar. So the pH equals minus a negative 4.0, and therefore the pH itself is 4.0. When we negate a negative, we get a positive value. If you end up with a negative, remember in our course that should be a red flag because we said we would stick between 0 and 14 for our pH values. So you should never have to worry about a negative pH here, but if you go on in chemistry, certainly that will come up. All right, one more thing before we set you loose on calculating pH values. We have to consider significant figures. We started the course with this concept, and then a number of you have been fighting with me on those, in the lab in particular, for those lab reports since then. It's time that we're ending the course here that we revisit sig figs, because sig figs and pH are different than the sig fig rules we talked about so far for multiplication, division, subtraction, and addition. When we're expressing these log values, the number of decimal places in the pH is equal to the number of sig figs in the coefficient of the H3O plus concentration. So what I mean by that, if we look here at the actual values, if H3O plus is equal to 1 times 10 to the minus 4, the pH value will have 1 decimal place. So that one value in the coefficient, the 1 sig fig for the coefficient, results in 1 decimal place. If we look at the second example, H3O plus concentration equals 8.0 times 10 to the minus 6. These are molar concentrations, of course. The pH here would be 5.10. Since we had 2 sig figs in the coefficient, we now have 2 decimal places in the sig figs. So the pH value between 0 and 14, that value in the 1s and 10s place, doesn't affect our sig fig values. It's only the decimal places that are impacted. So finally, H3O plus of 2.4 times 10 to the minus 8. Again, we had 2 sig figs, the 2 and the 4 here in the coefficient, so we have 2 decimal places in our pH value of 7.62. So hopefully, if you've struggled with sig figs all semester, this is one last chance to get it right and make sure that you can apply sig figs here in the pH setting. Okay, whenever we start to calculate something, especially something that we're going to do many times, we have our guides here. And this is our guide to calculating pH in an aqueous solution. So we're water-based in this course. Next semester, if you stick around for the second half, where we do the organic and biochem, the organic chemistry sometimes happens in non-aqueous conditions, but general chemistry and biological chemistry, we're almost always in water. So number 1, we enter the H3O plus concentration. Number 2, we press the log key and then change the sign, right, because we're taking the negative log. So whatever we get for the log will likely be a negative value here in our course, but since we're taking the negative of that, we end up with a positive value. Finally, now that we know the sig fig rule, we adjust the number of sig figs on the right of the decimal point to equal the sig figs in the coefficient. So if we had 2 sig figs in the coefficient, we'll have 2 decimal places in our pH value. 3 sig figs in the coefficient, 3 decimal places in our pH, and so on and so forth. Okay, so let's work one together, and then of course you know what'll come after that. So here we're going to find the pH of a solution with an H3O plus concentration of 1.7 times 10 to the minus 3 molar. So first step, we'll enter the H3O plus concentration. So we enter 1.7, then on your calculator, depending on if it has an EE key or an EXP key, that's what you'll hit to reveal the exponential. You'll enter a 3 and then hit the plus minus key to change the sign so that it looks like 1.7 e minus 3 or 1.7 to the minus 0.3 power, however your calculator display might show it. Step number 2, we'll hit the log key and then change the sign. So once we hit the log key, we'll end up with a negative value, and then when we hit the plus minus key or just negate the negative to make it a positive, we'll end up with some number that has any number of digits displayed on the calculator, but we know better than just to copy those all over. Well, how do we know how many of those to copy over? Well, we just did our sig fig rule, right? So step 3, we're going to look for the number of sig figs in the coefficient, and in this case we had 2, right? It was 1.7 times 10 to the minus 3, so we know we're going to have 2 decimal places, and based on that calculator display value of 2.7695 blah 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 from the previous slide, we would round to 2.77 for our pH. So 2 decimal places based on our 2 sig figs. So the pH in this case is 2.77. Hopefully that was all comfortable, you worked along, and you're ready now to do it on your own. Okay, here it is, your chance to do it yourself. This learning check asks, what is the pH of coffee if the H3O plus concentration is 1 times 10 to the minus 5 molar? So go ahead and work this problem, and then based on those answer choices, decide which one is the best answer. Pause the video here while you do that, and then start back up when you're ready to check your work. All right, so the first step is to enter that H3O plus concentration. So you'd enter a 1, then hit your EE or EXP key, and then hit 5 and the negative plus minus sign to make it a negative value so that it looks something like one of those options in your calculator. Step 2, press that log key and then the plus minus key to change that result. And then we're ready for our next step here. Okay, so in our final step, we'll adjust the number of sig figs on the right of the decimal to equal the sig figs in the coefficient. So we had 1 sig fig in our coefficient, which means we have 1 decimal place here. So our pH is 5.0. This will give us answer C. And if you're already really catching on to this, what you probably noticed is the H3O plus concentration is greater than 1.0 or 1 times 10 to the minus 7 molar, which would be neutral pH. So if you knew that, looking at those answer choices, we had pH 5, pH 7, pH 9. Well, only pH 5 would have made sense. You didn't even have to do the calculation if you realized that you had something with a pH that was, or an H3O plus concentration rather, that was greater than neutral. So you knew that was going to be acidic to start. But we want to do it right. We want to do it rigorously, and hopefully you did. And you found that correct answer of choice C, pH equals 5.0. Okay, let's follow up with another learning check. This time we're told the H3O plus concentration of tomato juice is 2 times 10 to the minus 4 molar. What is the pH of the solution? And then we have a few answer choices. Go ahead, pause the video here, work the problem, and decide which answer choice is the best. And once you're ready to check your work, start us back up. Okay, so the first step is to enter that H3O plus concentration. This time it's not just a 1, it's a 2 value here. So hit the 2 key, then press EXP or EE, whichever your calculator has. You'll enter 4 and then use the plus minus key to change the sign. So your calculator display should look like one of those options there at the right. Step 2, you'll press the log key to change and then finally change the sign once you get the result. So you should end up something like 3.698, so on and so forth. Okay, now finally we're ready to adjust the value for sig fig. So we have 1 significant figure in the coefficient and therefore 1 decimal place of significance in our pH value. And if you do that correctly, you should find the pH is 3.7, answer B. Now, of course, only choice A and B made any sense because we knew that with a value of 2 times 10 to the minus 4 molar H3O plus concentration, we're greater than the 1 times 10 to the minus 7 molar H3O plus concentration for neutral solutions at 25 degrees Celsius. So choice C, that 10.3, that basic pH made no sense. And what you probably have noticed is since we weren't 1 or 1.0 times 10 to something, we don't end up with an exact value. So 4.0 would be the case if we were 1 times 10 to the minus 4 molar, but since we're 2, we end up with something different, something close, but something different here. In this case, a more acidic solution and therefore a lower pH of 3.7. So you could have used logic again, but hopefully since you're just getting the hang of this, you did it rigorously and came up with the correct answer of pH equals 3.7, answer choice B. Let's do one more learning check. This time we're looking at the OH minus concentration of a solution is 1.0 times 10 to the minus 3. What is the pH? and we have our answer choices there. So go ahead and stop the video here, try the problem, and start us back up once you're ready to check your work. All right, so the tricky part here was the fact that you were given the OH minus concentration instead of the H0 plus concentration. So step one is still to enter the H0 plus concentration, but since we're starting with OH minus, we have to calculate H3O plus. So if you recall from our last section, we found H3O plus and OH minus were related by Kw. So in this case, since we know the Kw for water, we're assuming it's 25 degrees Celsius here, which is a fair assumption to make in our course. So we know the value of the Kw is 1.0 times 10 to the minus 14. We know the value of the OH minus is 1.0 times 10 to the minus 3. And if we look at that relationship, Kw equals H3O plus concentration times OH minus concentration. To find H3O plus concentration, we divide Kw by OH minus. And in this case, if we do that correctly, you should end up with a value of 1.0 times 10 to the minus 11 for your H3O plus concentration. If you go ahead and put that in your calculator, 1.0 and then EE or EXP 11, then the plus minus key to make it negative 11, you end up with a calculator display of something like 1 to the minus 11 power, or 1 minus 11, or 1E minus 11. So hopefully it looks like one of those options. Okay, so if you correctly figured out step 1, step 2 and 3 should have been a breeze. Step 2, of course, we hit the log key and changed the sign. So we end up with 11. And finally, step 3, we adjust the number of sig figs to the right of the decimal point to equal the sig figs in the coefficient. Here we had 2 sig figs in the coefficient, so our pH value should be 11.00, which should relate to answer choice B as the best answer. So again, if you're still struggling after these learning checks, please do try some additional problems or get in touch with me for some help. Otherwise, let's move on. And so since that last learning check looked at the idea of calculating H0 plus from OH minus values, let's take a look here at how those relate to pH specifically. So if we're looking at the H0 plus concentration for a pH of 0, it would be 10 to the 0 power. And then the OH minus concentration would be 10 to the minus 14. As we move down the column for the H2O plus, we increase our exponential from 0 to the minus 1, so we're actually decreasing the H2O plus concentration, and our pH value is just that exponential as a positive value instead of a negative. Again, 0 is neither positive nor negative, so we end up with a pH of 0 from 10 to the 0, but 10 to the minus 1 all the way up to 10 to the minus 14 relates to a pH of 1 to 14. And notice that it's related in the reverse relationship with the OH minus, where the pH is 0 because 10 to the 0 is our H0 plus concentration. The OH minus concentration is 10 to the minus 14. And as we move down that column, our values go in the opposite direction as our H0 plus concentration, such that we always have our values add to 14, or negative 14 actually, if we just add the 10 to the negative whatever for H0 plus and 10 to the negative whatever for OH minus, because of that Kw value of 1 times 10 to the minus 14 is the Kw of water at 25 degrees Celsius. So hopefully if you haven't noticed that feature yet, this table has brought that out for you. So up until now, we've used H0 plus concentration to find pH. Let's go the other direction. This is our guide now to calculating H0 plus from the pH value. Instead of going from H0 plus to pH, now we're going from pH to H0 plus. So first we enter the pH value and change the sign. Then we convert the negative pH to concentration, and finally we adjust the sig figs in the coefficient. So that's our guide. Let's see how it works out with the sample problem. Okay, so here in our sample problem, we're asked to calculate the H0 plus concentration for a solution with a pH value of 8.25. So H0 plus concentration equals 1 times 10 to the negative pH So for a pH of 8.25, we're looking at an H3O plus concentration of 1 times 10 to the negative 8.25 power. So step 1, we enter the pH value and change the sign, right? So we take that 8.25 that was given and we make it a negative 8.25 because really it's 10 to the negative pH. Step number 2, we convert that negative pH to concentration. So you press the second function key and then press the 10 to the x key. It's usually the same as the log key because it's the anti-log. So looking there at how you do it, and then the calculator display should be 5.62 something 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 times 10 to the minus 9, depending on how your calculator displays that exponential. What you could also do is press the inverse key, and the log key is where you tend to be able to get that anti-log. So 10 to the x is the anti-base 10 log. Okay, now finally our third step is the same. We're adjusting for sig figs. In this case, we had 2 sig figs, 2 decimal places rather, in our pH value, so that relates to 2 sig figs in the coefficient. So this should be 5.6 times 10 to the minus 9 molar. It's not especially difficult. It's just the opposite operation compared to what we were doing before. If you're having trouble, you can't figure out how to do it on your calculator, if you could just send me a picture of your calculator keypad, I can give you a lot of good advice there. So if you had any trouble following along with us and you're just not sure where you went wrong, chances are it's how you put it into the calculator, and if you send me that screenshot there of your calculator keypad, I can give you advice on what your specific keys would be to enter, because it may be different or it just may be tough to figure it out from the directions here. Okay, so now that we've done that together, it's time for you to do one on your own. So before we leave section 4 here of chapter 10, the learning check that you'll complete asks what is the H3O plus concentration of a solution with a pH of 11.2. And then you have a number of options here, and it looks like this one's probably getting at the idea of sig figs, right? So hopefully you've been paying attention. All right, so go ahead and still solve it rigorously, and then you'll apply your sig fig rules, and you'll see probably that you could have answered it very quickly if you knew the sig figs. So why don't you go ahead and do that, and stop the video here, start back up when you're ready to check your work. Okay, so we're going to solve it rigorously, and then you're going to see how easy it was if you just knew your sig fig rules. So first, what is the H3O plus concentration? So we've got the pH. We'd enter the pH value and change its sign because, of course, the H3O plus concentration is equal to 10 to the negative pH value. So step 2, we'll convert that negative pH to concentration by pressing the second function key and then the 10 to the x key, or however you do it in your calculator, and you should end up with something like what you see there, 6.309, and so on and so forth. Now finally, in step 3, we'll adjust the sig figs in the coefficient based on the sig fig in the number of decimal places of the pH. So there we had just 1 decimal place and therefore just 1 sig fig. So your H3O plus concentration is equal to 6 times 10 to the minus 12 molar. So if you looked at the answer choices in this case and saw that they were all roughly the same value, just different sig figs, and you knew the sig fig rule, you could have picked that out pretty quickly and easily. But again, you're not always going to have that luxury, so it is important that you be able to do it yourself. And if you couldn't do it rigorously, please do reach out for some help after you've tried a couple more problems if you're still struggling. All right, but hopefully that's not the case. Hopefully everyone's doing super on this and you're eager to move into the next section here of chapter 10. So we'll see each other again very soon for that section.